So welcome everyone to the summer seminar series, Conversations with National Laboratories, hosted by the Department of Mechanical and Aerospace Engineering at Princeton University and organized by Professor Julia Mikhailova. Today we are happy to continue our conversation with Dr. Nate Ferraro from Princeton Plasma Physics Laboratory. Nate Ferraro is currently a principal research physicist in the theory department at PPPL. He was a graduate student at Princeton, 2003 to 2008, where he focused on magnetohydrodynamic simulations with his advisor, Steve Jordan. After graduating, he worked as a postdoc and staff scientist at General Atomics. General Atomics is a private company in San Diego that operates the largest magnetic fusion experiment in the US for the DOE. In 2015, Dr. Ferraro returned to PPL, where he is focused on modeling large-scale plasma stability in Princeton's magnetic fusion experiment, NSTX. Recently, Dr. Ferraro co-chaired the APS-DPP community planning process, which was organized to provide a long-range strategic plan for the DOE Office of Fusion Energy Sciences. We are very happy today to have Dr. Ferraro from PPPL to present his talk on accelerating fusion energy research at PPPL and around the world. As a reminder, please post any questions you have in the chat box, and you can also ask them live at the end of the talk. And with that, I'll turn the mic over to you, Dr. Ferraro. Thank you for being here.
Great, thank you very much, Nicholas, for the introduction, and thanks, Julia, for inviting me. Let me just try to share my screen here. Okay, I hope that's visible. So just like last week's presenter, my friend Ahmed Diallo, I'm a principal research physicist at the Princeton Plasma Physics Lab. I'm going to be talking, so I think Ahmed gave a good overview of what's going on at the lab. I'm going to focus in on the fusion research in particular, not just about what's going on at PPPL, but what's going on throughout the United States, what's going on internationally, and where this research is headed. So let me start with a brief introduction about fusion. And I see a number of my colleagues have joined, so they'll probably be able to chime in here as well if people have comments or questions. So fusion energy is really an ideal power source. How does fusion energy work? In fusion energy, you have basically light elements, in this case, deuterium and tritium. You fuse them together, and this reaction releases helium nucleus and a neutron, and quite a bit of energy, actually. This is actually a very energetic reaction. You can get a gigawatt week of energy from just 2 kilograms of fuel, which is really quite amazing if you think about it. So this is really an ideal power source. There's no greenhouse gases associated with fusion energy. No long-lived nuclear waste is produced. There's no possibility of meltdown. It produces high intensity baseline power, and the fuel is abundant and available to all nations. So with deuterium, I think about 1 in 6,000 hydrogen atoms is actually deuterium, and we think we can breed tritium from these reactions. So the only problem is fusion is hard to do. So fusion requires temperatures of about 100 million degrees, maybe a little bit more than that. And at these temperatures, obviously you can't confine something at that temperature by anything that's solid. And at these temperatures, matter becomes plasma. So atoms will break apart into ions and electrons. And here's a cartoon of what we're doing. We're basically dumping energy into the plasma to try to heat it up. There's continually energy being lost from the plasma, which is cooling it down. And if we get the plasma hot enough, then it's producing fusion energy, which we could then harness to produce electricity. And some of that fusion energy actually comes back and heats the plasma up. So this, if you're producing enough fusion energy, this can actually become a self-sustaining reaction, which would be called a burning plasma. So the fundamental challenge that we're dealing with is how do we confine this plasma at 100 million degrees long enough to get more fusion power out than the power we're putting into it. So not only do we need more fusion power out than power in, but we also need enough surplus to make this an economical thing. The goal of this is to be a power plant where we sell electricity. Even if you can do this at some really expensive cost at some giant scale, that's not going to be helpful. We need to make this something that's economical and commercializable. So there are basically two approaches to fusion energy, broadly speaking. There's what we would call inertial fusion energy. So this is where we take a small pellet that you can see here. This is actually called a whole room, which would encapsulate the pellet. You then shoot lasers into this whole room. It creates X-rays that then compress the fusion deuterium-tritium fuel that's inside this whole room. It compresses it, and basically it explodes. It creates lots of fusion energy in a short amount of time. And the plasma is only confined for about 10 nanoseconds or so, but that's all you need in principle to burn up most of that fusion fuel. The main application for this is actually national defense, since this process somewhat mirrors what happens in a thermonuclear weapon. But there are ideas about how to extend this and turn this actually into a power source. The other approach, and the one we do for the most part at Princeton Plasma Physics Lab, is magnetic fusion energy. So this is where we're confining the plasma using magnetic fields. So in a reactor, the plasma would be confined continuously for hours at least. Here's a picture of NSTX, which is an experiment at the Princeton Plasma Physics Lab. And here's a picture of the plasma in operation. All of the Department of Energy funded research is MFE, magnetic fusion energy concepts. So how does this work? MFE works by confining the plasma with magnetic fields. So because the atoms have dissociated into ions and electrons, it becomes electrically conducting. The ions and the electrons can travel along magnetic fields, but not across them. So you can see the trajectory of an ion in this picture here. Here's the magnetic field line. The ion can travel along it, but if it tries to travel across it, it spirals like this. So this means that the thermal conduction is highly anisotropic. You get thermal conduction along field lines, but not across the field lines. So by making sure our magnetic fields lie on closed surfaces, particles are well confined to those surfaces. So you can see here a schematic of what those surfaces look like. So these would be the field lines on the surfaces wrapping around these toroidal surfaces. And the particles are confined to these toroidal surfaces. So they'll be, and of course these surfaces continue all the way around. Here it's cut through is shown, so you can see that these surfaces are actually nested here. And topologically, these surfaces must be toroidal so that the surfaces close on themselves. So many configurations, magnetic field configurations have been considered. But I would say that the top contenders right now, and where the lion's share of the research is being done, is in tokamaks in particular, and also in stellarators. So here's a picture of a tokamak, and here's a schematic of a stellarator. In a tokamak, the magnetic field is partially generated by the electrical current in the plasma itself. So you have external magnetic coils, which produce a magnetic field that goes around in this direction called toroidally. And you're also driving a current in the plasma in the toroidal direction. And that's creating a magnetic field that goes around poloidally. And this combination of fields can actually do a good job confining the plasma. Now this current is typically driven inductively. So you can see in this picture, and I hope you can all see my mouse. In this picture, you see this central green coil here is a solenoid in which we ramp the current. And ramping that current produces a loop voltage, an EMF, or toroidally around the plasma, which is driving the current. Now this is not inherently steady state because you can only ramp this current so high before you can't ramp it any higher. So these are inherently sort of pulsed concept, but it has many very good properties. It has excellent confinement. The magnetic geometry is actually very flexible in tokamaks. A downside is that it tends to be prone to instabilities, and I'll talk more about these a little bit later. Alternatively are stellarators, where the idea is that all of the magnetic field, or almost all of the magnetic field, is generated by external magnets. So this has the advantage that it's very stable and it's inherently steady state. It also has some disadvantages in that the coils tend to be fairly complicated. Not only are they hard to produce, but they tend to obstruct the plasma access from other diagnostics and actuators. And so far, stellarators, at least compared to tokamaks, have had relatively mediocre confinement. So what are the major challenges that we're trying to address? For tokamaks, I would say the major challenges, and there are more beyond these, but I think these are the major ones, are first, how can we prevent or mitigate disruptive instabilities? So that means the instabilities that form that actually terminate the plasma discharge. This is a big problem in tokamaks, and we have to solve this for it to be a realistic reactor concept. Another question is, how do we sustain steady state operation? As I said, that driving the current inductively is very efficient, but it's also inherently not steady state. So can we figure out how to do it steady state, or can we figure out how to live with a pulsed reactor? There are problems associated with that too. We have to figure out one or the other. For stellarators, the question would be, can we achieve or exceed even tokamak-like confinement by optimizing the magnetic geometry? And can we do this with a magnetic coil design that is sufficiently simple? So these, I would say, are the main questions for these two concepts in particular. But any configuration that you pick, whether they're tokamaks, stellarators, or something else, also has to deal with a number of other questions. In particular, how do we handle high power flux to the plasma-facing surfaces? So the plasma is obviously very, very hot, and you're delivering a lot of heat flux to the surfaces that surround it. So how do you deal with that for long periods of time? Another question is, how do we breed tritium? We'd like to be using deuterium and tritium, but tritium doesn't really occur naturally, so we have to be breeding it. Can we breed enough of it, and how do we breed enough of it? We think we can, but we have to demonstrate this. And then what materials will perform well in a fusion nuclear environment? So the fusion reactions are putting out neutrons. This is not inherently a bad thing. We can use those neutrons, we can capture them to heat our blankets to generate electricity. But of course, when neutrons are hitting things, they can degrade material properties. So we have to figure out how to deal with that. So let me make a quick note about how is fusion actually funded in the US. So in the United States, fusion energy research is primarily funded by the Department of Energy, Office of Fusion Energy Sciences. So this is quite a large program, over $500 million in fiscal year 19. This includes more than $1 million for construction of ITER, which is a large experimental reactor being built in France. And I'll have a little bit more to say about ITER later. Funding sort of fluctuates based on the priorities of the Department of Energy and Congress, but right now it's been, the past few years have actually been quite good for fusion energy research. There's been, I would say, a significant upswing over the past few years. So the Department of Energy operates two fusion user facilities, one of which is at PPPL. That facility is called NSTXU. That is a spherical torus, or you saw a picture of it a couple slides ago. It's basically a tokamak that's a little bit more compact shape than a typical tokamak. And the other user facility is called D3D. That's a tokamak at General Atomics. And General Atomics is a private company in San Diego. So the Department of Energy also supports fusion research at many universities, and I have a list of some of the universities that receive the most support here, but there are actually many universities that receive support for fusion energy research. There's also, interestingly, over the past few years, there's really been significant new investment from private industry. So TAE is a company in Irvine that's privately funded for making, they've got their own concept, which is not a tokamak and it's not a stellarator. They have a field reverse configuration. And there's a company, Commonwealth Fusion Systems, which is another fairly large company that was formed by basically by graduate students from MIT that is pursuing high temperature superconducting concepts. So there is now actually a Fusion Industry Association, which is a trade group representing more than 20 private fusion company members. So this is a new development. There's actually a lot of private money coming into fusion research now and a lot of startup companies now, which is a big change in the landscape. So Princeton Plasma Physics Lab, again, this is something that Ahmed talked about, I think in detail last week. So I won't go too much over everything that's done at the Princeton Plasma Physics Lab, but Princeton, the Project Matterhorn started at Princeton back in 1951 by Lyman Spitzer. In 1961, that became Princeton Plasma Physics Lab, which much of which is pictured in this picture, but actually some of the major facilities would be off to the left here. It actually has quite enormous infrastructure capabilities for fusion energy experiments. Presently employs more than 500 people. It has a budget of more than $100 million, which is roughly a third of Princeton University's total research budget. And research includes not only fusion energy, but all sorts of other plasma physics related stuff, plasma astrophysics, low temperature plasmas, high energy density physics, and fundamental plasma physics. So let me just take a minute to describe my own career and some of my research. So I got my bachelor's degree and my master's degree from Dartmouth. The reasoning for me going into fusion energy was actually a little bit serendipitous. So Dartmouth has a big space plasma physics program. Many of the faculty there are doing space plasma physics, mostly experimental, launching rockets into the magnetosphere and the aurora and stuff like that. I was looking for an intersection of the strengths of that program with my own interests in energy research and physics. Of course, I was a physics major, and that was I thought fusion energy. So I did a senior thesis with my advisor there, Barrett Rogers, who at that time was a new faculty member at Dartmouth. I applied for some for grad school, a couple of places to do fusion research. Didn't get in to any of those places, so I took another year to get my master's degree at Dartmouth, so I would have more experience with plasma physics. And I did that, and then I got into to Princeton, where I was from 2003 to 2008 to do my PhD. So my first year was an experimental project with Sam Cohen. He's got a field reverse configuration, and I was doing spectroscopy to try to measure the density and temperature of the plasma in his device. After that, I started working with Steve Jardin, doing MHD modeling. So this is magnetohydrodynamics, and I'll talk about this in a couple slides, mainly for tokamaks. And I dabbled a little bit in basic and space plasma physics, looking at the magnetorotational instability for one thing. So after that, I took a postdoc at General Atomics, which is this company in San Diego that I mentioned before, which operates D3D. I was a postdoc there for 3 years and then a staff scientist there for 5 more years. I was doing modeling of equilibrium and stability of tokamaks there, similar to what I was doing as a grad student. And then in 2015, I moved back to PPPL, where I've been doing still sort of similar things, modeling of tokamak stability and equilibria, focusing on theory and experimental collaboration. One thing I did over the past year and a half, which I'll talk more about in a few slides, is I was a co-chair of this APS DPP community planning process. And this was fairly extensive process to provide community input in forming a long-range strategic plan for the DOE Office of Fusion Energy Science. This long-range strategic planning is an activity that's going on now, and we expect this to be finished up by the end of this year. So we'll actually know quite a bit more about the long-range strategic plan for Office of Fusion Energy Sciences fairly soon. So let me just mention M3DC1. So this is a code that I started working on as a grad student, and it's sort of been with me since that time. It's been a very flexible and adaptable code that we've applied to a lot of different problems. So M3DC1 was a code that was initially developed by Steve Jardin and me while I was a grad student. A number of other people made substantial contributions during that time, so I don't want to leave them out. This is a parallel finite element code. It's mostly in Fortran, sadly, but actually it's we've been able to develop it and extend it pretty well. It is an extended magnetohydrodynamics model. What this means basically is that we're treating the plasma as a compressible conducting fluid. So it's fluid equations plus Maxwell's equations is basically it. Plus a bunch of other effects like resistivity and viscosity and anisotropic thermal conductivity. But basically this is it. It's treating the plasma as a fluid and evolving Maxwell's equations. So the development of this code has really focused on addressing macroscopic stability in tokamaks. And now M3DC1 is considered a flagship code at PPPL. It has roughly 20 active users, maybe a little bit more than that at multiple institutions. That doesn't sound like a whole lot, and it's not, but it's a very specialized activity. And it's a very useful code that's being applied to many different things. Now, a couple of things that I've applied this code to, I'll just briefly touch on some of these. I don't want to get too much into the technical details. One is edge localized modes. This is a challenge for tokamaks. So in the high confinement mode of operation, which is called H mode, tokamaks have this, what's called a pedestal in their pressure profile at the edge. The pedestal is just a very narrow region of very steep pressure gradients. Now this is sort of a great thing for tokamaks because this means you have really good confinement at the edge. So you're really holding the heat in very well. The problem is as the edge pressure builds up, eventually it becomes unstable and you get this thing called an edge localized mode. And you can see a picture of it here. Now this doesn't terminate the plasma. It's sort of benign in existing devices. But you can see that it's periodic. So the pedestal will build up. You'll get this elm crash, which you see here by the spike, measuring the ionization and the sort of at the edge of the plasma. And then the pedestal collapses. It builds back up, goes unstable. You get another elm, etc. You just keep repeating. In present day devices, this isn't really a problem. But in reactor scale devices, this will be a problem because reactor scale devices, the amount of energy released by each elm will be so great that it will probably melt the plasma facing surfaces on those reactors. So this is something that we have to figure out how to address. So there is actually a solution that we found. If we apply three-dimensional magnetic fields, so fields that break that symmetry in the toroidal direction of the tokamak, it suppresses elms. And you can see here's a plasma. This is a plasma in D3D at General Atomics. And they have these coils called I coils. You can see there's one up here, one down here. These I coils are actually an array of coils. So as you go around toroidally, there's 6 different coils. And by alternating the currents in these coils, you can produce some 3-dimensional magnetic field. And what they find experimentally is when you do this, if you don't turn on the coils, you get your elms. If you do turn on the coils here at the green line, suddenly the elms go away. So this is great. The problem is it only works under certain conditions and only on some machines. And we don't fully understand why. And we don't fully understand, even on one machine, when it will work. So will this work in reactor scale tokamaks? We sure hope so, but we're not sure. So we need a predictive model of RMP elm suppression. I should say that these 3D fields are usually called resonant magnetic perturbations, or RMPs in this context. So we can apply M3DC1 to this problem to calculate, well, what does the plasma equilibrium look like when you've applied these 3D fields? This is actually quite a challenging problem because the response currents, so electrical currents will form in the plasma in response to applying those fields. Those response currents are actually strongly modify the shape of the plasma. So the response currents can actually be more important than the fields that you apply to start with in determining the topology of the magnetic field. So our calculations actually show a significant change to the magnetic topology near the top of the pedestal. So what this plot here is showing, this is called a Poincare plot. And what it's showing is if you look at a cut through the torus, like you're doing here, and you unroll these surfaces, you'll see basically straight lines. And if you, indicating the surfaces. And if you add a 3D perturbation, then you get ripples and corrugations in these surfaces, like you see here. In some cases, you can actually get a change in the topology of the magnetic field. So the magnetic surfaces actually break up and you get these things called magnetic islands, which can significantly enhance the transport. So this is something that might be preventing the pedestal from growing. Our research currently focuses on quantifying the thermal transport that's caused by these magnetic islands to see when do they get big enough to actually stop the pedestal from growing large enough for this Helm stability threshold to be exceeded. So just briefly, another topic that I mentioned before that we're applying M3DC1 to is disruptions. So disruptions are an uncontrolled loss of plasma current and confinement. There's many different causes for disruptions. There can be large-scale instabilities. For example, if you run too much current in your plasma, you can get one of these instabilities. There can be loss of position control. So we're constantly feeding back on the plasma position to keep it centered in the vessel. If you lose control, the plasma can drift off and hit the wall. This is called a vertical displacement event. Or you can just get a radiative collapse, like you can get a flake of something falls into the plasma, radiates out all the energy, and you lose all your thermal energy in the plasma. The problem with these is they can cause serious damage. So you can cause huge forces, tens of meganewtons, and huge thermal fluxes, tens of megawatts per square meter in reactor scale tokamaks. In addition, these rapid changes in the current density can lead to large electric fields, which can actually generate high energy electron beams. And that's what you see in this picture here. One of these electron beams has formed and is smacking into some carbon tiles on the surface of this tokamak. And that's something you don't want to see in your tokamak. So understanding and mitigating disruptions is a top priority of MFE research. So our focus has been on understanding how do you do disruption mitigation. So the reason the large forces are forming is because the plasma current is moving. The plasma current, which is shown here, in this case, this is a VDE, so the plasma is drifting down and hitting the wall. As it moves, first of all, it's touching the wall, so you're getting current flowing from the plasma into the wall and back out. And second of all, as the current moves, you're inducing large currents in the wall. So both sources of currents are causing large J cross B forces. So this is why you're getting these very large forces. So what we'd like to do is mitigation, which means we seek to cool the plasma rapidly as soon as it goes unstable. So this will lower the temperature of the plasma. It turns out that in plasmas, the lower your temperature, the higher the resistivity. So this will raise the resistivity, the current will decay away quickly, and hopefully you decay away most of your current before it moves significantly. So this mitigation strategy is usually done by injecting gas that cools the plasma either through dilution or radiation or both. So our research focuses on how do you optimize this? Can we reduce the forces without causing other instabilities or generating these high energy electron beams? How much should we be injecting and where? And actually, when should we be injecting it? We actually can't afford to fail many times on a reactor scale tokamak. We don't want to be producing these huge forces in a reactor scale tokamak too many times for obvious reasons. And you can see here, here's some simulations of an unmitigated disruption where the plasma is drifting down. And here's a simulation of a mitigated disruption. Actually, we probably injected too much gas in this case because we're creating this other instability, which looks interesting, but maybe that's not exactly what you want to happen when you do mitigation. Okay, so finally, let me spend a couple of slides talking about where I think fusion energy research is heading. So there are major new international facilities being built right now. W7X, Wendelstein 7X, is a giant multi-billion euro stellarator that was recently built in Germany. This has been operating for a few years now. Here's a picture of it from a few years ago. The goal of this stellarator is basically to test whether a particular type of stellarator optimization can yield confinement that approaches what is seen in tokamaks. That's one of the main missions of this. There's other, and I should say it's been producing actually very impressive results. And they're upgrading it this past year and are going to bring it online again soon. So there should be very new, interesting results coming soon. There are also in the works several large high-powered tokamaks worldwide being designed or constructed for specific research topics. So these include JT60SA in Japan, diverted test tokamak in Italy, CFETR, which is designed to test material properties in China. And then the biggest of all of these is ITER, which is shown in the bottom right figure there. ITER is supposed to come online initially in 2025. This is another multi-billion-dollar collaboration between 7 different entities: EU, China, India, Japan, Russia, South Korea, and US. The goal is to achieve Q equals 10, so 10 times more fusion energy out than power put into it. So this would be a first demonstration that we can actually achieve this. Over the past couple of years, as I mentioned, there have been some private companies entering the picture here. And now there are actually some designs from private companies for Q greater than 1 facilities. So there's Commonwealth Fusion Systems and Tokamak Energy. Both have plans for tokamaks using high temperature superconductors that they think could achieve Q greater than 1. So these are things to keep an eye on as well. So I would say that US is making a renewed push for fusion energy. In the 70s, energy insecurity and the promising results from fusion research led to major investments in fusion research. There were very rapid advances in technical capabilities, culminating with the design and construction of TFTR, which is a very large tokamak that could use deuterium and tritium at PPPL. And you can see if you look at a plot of, this is NT tau, which is basically the pressure times the energy confinement time in your tokamak, you can see this basically followed a Moore's law trajectory all the way up to these very large experiments, TFTR at PPPL and JET in England. In the 90s, the US changed their approach to fusion research. This was, this was great, but this was actually turning out, this progress was turning out to be a little harder than people expected. So there was a change of focus. TFTR was decommissioned, and the focus moved from these rapid technical advances to take a step back and make sure we had a solid scientific understanding so that we could confidently project further up this line. And you can see that sort of had the effect. We haven't had many new facilities during that time. We've sort of taken a step back. But in my sense, there's a real feeling among the community and among policymakers that we've learned so much in this past time that we're ready to take another push for fusion energy. So the US strategy is shifting towards power demonstration, it seems. And we'll know more about this as the long-range planning activity wraps up in this next year. But two major long-range planning activities leading up to this one have recommended a transition to an energy mission-driven program. So there was a National Academies report in 2018, Strategic Plan for US Burning Plasma Research, which says the following: recent advances motivate a new national research program leading to the construction of a compact fusion pilot plant. By starting now, a national research program toward a compact pilot plant and critical science and technology research can be ready in time to use the knowledge learned from ITER operation to demonstrate electricity production by mid-century. And I've bolded this myself. This is not bolded in the report. Following that, there was the APS DPP community planning process. This is the process that I mentioned I was a co-chair of. This put out a big report, a community plan for fusion energy and discovery plasma science. This process was a really extensive series of meetings intended to gather community input for long-range strategic plan for FES. So this not only affirmed the National Academy's major findings described here and in this report, but gave a prioritized list of research opportunities to achieve that. So both reports had major findings that included that the mission of fusion energy research in the US should be to enable the construction of this pilot plant. It should be a low-cost plant so that's something that could extrapolate to something that's commercializable. But the crucial part of this pilot plant is that it generates net electricity and demonstrates tritium breeding. And net electricity here is seen as the most important thing, I think. So in order to achieve this, both reports find that the scope of fusion research is ready to expand to include material science and technology development. This doesn't mean that we're done with plasma physics. There's still a lot there, both with ELMs, disruptions, and other things. But we're ready at this point to expand, to take on that material science and associated technologies. So I would say looking forward, when we're thinking about where is the research going to expand towards, I would say it's expanding sort of outwards as you look at a plasma, you know, as you look at an experiment as a reactor, it's expanding outwards. So the core plasma research was the original focus. So this is where over the past decades we've been spending most of our attention. And there's still important problems to solve here in terms of optimizing magnetic field configurations, understanding macroscopic stability, turbulent transport properties. These are all very important issues. But now we're seeing an expansion into plasma material interaction. How do you deal with the plasma? How do you deal with the heat that's coming out of the plasma incident onto these plasma-facing components? How do you deal with sputtering, erosion, neutron displacement damage, helium implantation? And it's my feeling that the next major facilities in this country will likely target these issues to a large extent. The development of the enabling technologies that are necessary, sort of illustrated in this exterior circle here, I think are also likely to expand. This is probably a little bit farther off, but we need to explore how to breed tritium with our blankets that surround the plasma. Superconductors, high temperature superconductors in particular, are actually a topic of a lot of ongoing research. RF power systems for heating and controlling the plasma, pumping systems, all of these kind of things are going to need attention when we talk about designing a reactor that can produce power commercially. Complementing all of this and enabling all of this, I should also mention that there's been a very large focus on high performance computing within the Department of Energy. This has really enabled a lot of new science and has been providing a lot of opportunities for modeling. So there are major initiatives on machine learning, exascale computing, and even quantum computing coming out of the Department of Energy right now. So there's lots of opportunities there. And I think that's the final takeaway I want to leave people with here. There are lots of opportunities to get involved in fusion energy research right now. It's not just for plasma physicists. So I thank you all for your attention, and I'll be happy to take questions.
Thank you so much. It was a really great talk. So please post your questions in the chat box, everyone who wants to ask a question. So I want to ask a first question. You mentioned machine learning in your last slide. Is it useful in your research? Do you use any AI tools or?
I haven't personally, but yes, in the areas of research that I'm involved in, there's a lot of research in machine learning. So I would say there's sort of two flavors. One is machine learning where the algorithms are trained on experimental data. So for example, disruption prediction. Can you feed data on disruptions that's obtained from experiments into a machine learning algorithm and have it be able to predict when your plasma is about to disrupt? There's a number of different groups that are doing this, and this is showing some promise. Another area where machine learning is used is just in making modeling more efficient. So you can train a machine learning algorithm on not the output of experiments, but actually the output of simulations, so that you can, rather than running a very expensive nonlinear turbulent simulation, for example, you'll have trained this algorithm on a set of these things that you've done in advance, and you can actually predict what the answer would be by interpolating using machine learning. And I'm sure there's many other examples of where machine learning can be used, but I would sort of put them in those two categories.
What about your code, M3D-C1?
Yeah.
Can it run on GPUs? I heard you have a new cluster at PPPL, which has a lot of GPUs in it.
Yeah, so we've got this new cluster called Traverse, which is one of these hybrid CPU-GPU models, and we're porting it there now. So so it does run using GPUs. I wouldn't say that we've really optimized it very well yet, but we're just learning how to do this. We haven't seen tremendous speed up yet, but I think we have a lot to do before we can, to optimize it for that kind of architecture.
Thank you. Another question is, what are the main factors that affect energy confinement time in different devices?
Well, probably the main factor is just the size of the device. So if I can, maybe I can go up to the very top here. This answer isn't the most interesting, but the size plays a major role, because the rate at which you're losing energy is proportional to the surface area of the plasma, and the total energy in the plasma is proportional to the volume. So as you get bigger and bigger and bigger, the ratio of stored energy to energy loss, which is the energy confinement time. Well, okay, that's not quite the energy confinement time, but it basically scales with the radius. Of course, if you have poor energy confinement time and you're trying to scale up to something that could be a commercial reactor, you'll find that you need to scale it up to tens of, or maybe 100 meters or something like that, which is just not practical. So you need to find other ways of improving your energy confinement time. Now we're learning a lot about how energy confinement time can be improved both in tokamaks and accelerators. Tokamaks generally have pretty good energy confinement time, especially when they're operating in this high confinement mode of operation. The high confinement mode, if I can get back to this picture here and move my, I hope my window here isn't blocking too much of what you're seeing. So this gradient here is really supported by, we think, is supported by shear in the flow of the plasma. So there's some sort of velocity shear going on in the plasma. You can get strong velocity shear in a tokamak, it turns out, because of the symmetry properties of a tokamak. You have symmetry in the toroidal direction, which means you have no damping of the flow, theoretically no damping of the flow in the toroidal direction. So you can get this strong velocity shear in the edge, and that supports that breaks up turbulent eddies and supports a very steep gradient. So that's one way of improving your energy confinement time in a tokamak. Now we apply the same principle in a stellarator, and that's what's leading to these new ideas about stellarator optimization. So in particular, there's an idea of not perfect symmetry in a stellarator, but something called quasi-symmetry. And it turns out that if the magnitude of the magnetic field, so the total magnitude as opposed to any particular component, if that magnitude also has some symmetry, so if that magnitude doesn't change toroidally, for example, then you get all the good properties of actual symmetry from the standpoint of the plasma rotation. So there was a device that was designed and started to be built at PPPL called NCSX, which was a quasi-axisymmetric device, which meant the magnitude of the magnetic field didn't change as you went around toroidally. And the idea was that you would get you'd be able to get these same kind of shear flows that could support these steep pressure gradients. That's something that still hasn't really been tested yet. That device was never completed, and we still haven't tested this concept. So this is, this W7X device, if I can get back there, this is not quasi-symmetric. This doesn't test that kind of concept. But we think at PPPL that this is a very promising concept that we'd like to test to see if we can improve the energy confinement time in stellarators using that concept.
Thank you. We have several questions which touch upon your experience in industry and university and national lab. So perhaps our first question is, what sorts of factors does one consider when deciding whether to do plasma fusion research in a national lab versus a private startup versus at a university? How does one choose what sort of avenue to pursue?
Yeah, this is, I had an extra slide on this because I expected to get that kind of question. So I've worked in private industry and also at research labs, well, at a research lab at PPPL. And of course, I've also been at a university as a student. I would say that at research labs, so there is a big difference between research labs and what we would typically describe as private industry. The private companies that I'm thinking of here would be something like TAE in California, or CF, Commonwealth Fusion Systems at MIT, or these other startups. So in these settings, I would say the focus is really on rapid development cycle, meeting milestones set by your sponsors. And I would say you don't really have time to go deeply into science in these cases. This is much more of a startup environment. There's high risk, low inertia in research. You can change your research direction on a dime. The idea is to fail fast. So you test something. If it doesn't work right away, you throw it away, you take a new direction. So the goal is really achieving these technical progress. Research labs, there's more variety probably depending on what group you're part of, but I would say it's sort of the opposite of that. There's relatively low risk tolerance. This is all government funded research. Everything you do has to go, goes through peer review, multiple levels of peer review, goes through, you have to be responsive to solicitations from the government, that kind of thing. So it's relatively low risk tolerance. You have much more inertia in the research. So projects will go on for much longer. You do have a broad range of team sizes and structures. So you do have some very large teams like you do at D3D and NSTXU, and you have some very small teams that can be more nimble. There's a great advantage, I think, working at a research lab. is in that you're not required to be obtaining funding through grants all the time to maintain your employment. So you don't have to keep, you don't have to keep writing grant proposals and that kind of stuff. You can be part of a bigger team. This doesn't mean you can't do that. You're still encouraged to do that, but you don't have to do that. I would say my experience at General Atomics, so General Atomics is a private company, but it is funded by DOE. All of its, basically everything it does with regard to D3D is through DOE. So it actually operates very similar to how a national lab operates. The focus is on, there's a lot of inertia in that experiment. So D3D has been running since 1986. The focus is on publishing papers and all that kind of thing. So General Atomics is kind of an anomaly. You don't have many companies like this operating in this way, operating a DOE national lab. But I would say General Atomics, my experience there was actually fairly similar to what it is at PPPL. And then of course there's universities. I'm probably not the best qualified person to speak about what it's like to be a professor or a research scientist at a university. In the field of fusion energy research, many of the research scientist positions at universities are actually cited at national labs. So you have a lot of people, University of Wisconsin, University of California, research scientists that are actually cited at General Atomics working on D3D, or cited at PPPL working on NSTXU. And another thing to consider is that in plasma physics in particular, if that's your specialty, there are relatively few faculty positions. There aren't that many universities that have plasma physics programs. So it can be, if you're looking for to be a tenured professor in plasma physics, that can be, it can be a great job, but it can be a difficult job to find.
Thank you very much. A related question, is there more, where did you have more research freedom? For example, I heard Bell Labs, they were such a wonderful place to work in, because many people say we have money and freedom here, and this is all what the scientist needs. So where did you have more freedom?
Well, I've been pretty fortunate in my career that I've been basically allowed to do pretty much what I wanted to do. And I would say the most freedom I've had, though, was as a grad student or as a postdoc, when things were just totally wide open and I could go whatever direction I wanted. I feel like I still have that freedom in some sense, but as I get farther in my career, I've got more and more commitments. I have milestones that I have to meet. I've got grants and that kind of thing that I'm responsible for. So it just becomes harder to change direction. That's my own personal experience, and I know a lot of other people don't have that same experience. I think it really depends on what is the team that you've become part of. What is your actual situation? It's not necessarily are you working at PPPL or are you working at a private company or something like that. I think it's a little bit more fine-grained than that. So on a bigger team, on something like, say that you're working on NSTXU, you might have a responsibility as a diagnostics operator for something that people are counting on you for doing, and that makes it more difficult for you to change directions. I guess thinking about it now, I also have a similar thing with M30C1. I think this has been, the success of M30C1, I think has been a very good thing for my career in general. But I think that also because there are a lot of people that are dependent on it now, I feel that obligation to keep supporting it, to make sure that it's there for people when they need it.
Thank you. And where do you have more job security?
I would say that the job security is the highest at a national lab, I would say, something like at PPPL. the funding is relatively stable, even though there are fluctuations depending on the the priorities of Congress in a particular year. It's good jobs with good benefits, and it's not that easy just to hire and get rid of people. At General Atomics, it was sort of similar. General Atomics is a private company, so they had at-risk, at-will contracts that they could fire you at any time for any reason, which, it made it a little bit more nimble for them, but it also made your job a little bit less secure. I would say, the other end of that is probably these private startups. These are something where the money can disappear right away. But on the other hand, looking at something like TAE in California, those guys have been around for a long time, getting pretty steady research, or pretty steady funding. So, but overall, I would say at the National Lab, you have the most, and of course, being a tenured professor, you have very good job stability, of course.
Thank you. Andreas Giacos wanted to ask a question live.
Yeah, hi. I had two quick questions to ask. First was in regards to private industry and investors you were talking about. So I know PPPL gets private investors, but do these affect your current research in any way, or very much?
They're starting to more and more, actually, because there's been a lot of interest in private companies. There's been a lot of interest in figuring out how to couple those private interests with the capabilities of the national labs. So a lot of these companies look at the capabilities we have at PPPL and say, how do we contract out for some of the expertise or some of the capabilities at PPPL to use them for our own research? So there have been actually now a number of initiatives to basically to work out that interaction. And I think, I don't know how much, I didn't see all of Ahmed's talk last week, but Ahmed is in charge of this Infuse program at PPPL, which is actually a way of facilitating the interaction between the private companies and national labs. So this would be just what I described, where it is a private company comes with some amount of money and some desire to use PPPL resources, and that goes through a peer review process. And if it's successful, then they get to use some national lab resources for their own activities. So this has been happening more and more at PPPL. So there are definitely opportunities to do that, but there's no obligation as a research scientist at PPPL to do that.
Thank you. And the other question was in regards to your experience at PPPL collaborating with other institutions. Do you do that quite often, or are you more close-knit within the PPPL community?
Yeah, there's a lot of collaboration all the time. So since I was at General Atomics, I have a lot of contacts out there, and I still collaborate with them very frequently. PPPL is involved in research all over the world. So there's very strong connections with W7X in Germany, with tokamaks in South Korea and China. So there are, and a very strong connection with Oak Ridge National Lab. So I would say there's a lot of opportunity to collaborate outside of PPPL.
Thank you.
Thank you very much. There is a related question. Is there a strong competition in fusion research between different facilities? Do people share data, codes? Yeah,
I would say it's a very collaborative environment. So there's lots of sharing. M3DC1 is available for anyone to use it. All of the data from D3D, from NSTXU is available for anyone to use it, provided they agree to the data management, data use policies or whatever. But this is all Department of Energy funded research. So, I don't think people would try to hide that stuff anyway, but because it's Department of Energy research, we have an obligation to make this all available for other people to use.
Thank you. And another related question. Is it easy to publish when working for General Atomics? I guess this means is there some confidential information that?
There's not really confidential information. They do have internal R&D projects which are confidential when they're being done, but that makes up a small fraction of what they're actually doing. Most of it is externally funded DOE research. General Atomics has a little bit more rigorous process for getting your publications out. So you don't just write a paper and submit it. You write a paper and send it to the publications group at General Atomics. It then goes through some internal peer review processes at General Atomics. And then assuming that's successful, then you can publish the paper. Now they try not to make it too onerous because at General Atomics, just like at PPPL, their programs are judged in part by how many papers they're publishing. So they don't want to make it really hard to publish. I think it's more of a quality control issue. And this, something similar actually exists at PPPL, not quite to the same extent, but they do encourage at PPPL for any publication to go through an internal review process, especially if you're publishing something with NSTXU data, for example.
Thank you. Another question, do you know the landscape for the number of careers at PPPL within the next year due to COVID?
Due to COVID, it's hard to predict. So first of all, I don't really have a good sense of how many people we're planning to hire at PPPL. Our lab director, Steve Cowley, has ambitious plans, which I think are great, about PPPL expanding to include or to be stronger in other areas, including microelectronics, things like that. So I think Steve would really like to see PPPL expand to be twice its size within the next 10 years, certainly. If that can be achieved, that would be phenomenal. I don't know the chances of that happening, but I certainly support that. With respect to COVID, it's hard to predict exactly how that's going to affect the lab. Of course, the government is spending a lot of money on boosting the economy with COVID going on. On the one hand, that at least in the near term, that probably means that they're not going to be trying to pull money away from PPPL. This is a way of supporting jobs, and the government realizes that. In the longer term, if there are big deficits or something because of this and sustained, then you might see a pullback on how much the government is spending. But this is all, totally speculative and will very much depend on what Congress looks like and what the administration looks like and other external factors. So it's kind of hard to predict.
Thank you. And perhaps the last question, what advice can you give to someone who wants to work on fusion? To a graduate student, for example, who wants to work on fusion in the next few years?
Well, I would say I hope you do. There's lots of different things to work on, and I think fusion is such a diverse field. There's such a diverse range of disciplines that have to get involved for fusion to be commercially successful, that I think anyone with any background in physics or engineering would be able to find a place within fusion research. And some of those places might be small now, but like I said, I really expect some of those places to be expanding in the near future. So if you have if you have a passion for fusion energy, which I do, I really support the cause of fusion energy, and you're a technically inclined person, I think it's a great career path. It's a great thing to be spending your time doing. And I'm proud to do fusion energy research, and I enjoy doing fusion energy research. I feel like what I'm doing is making an impact. So, and with any job, I would say you should feel like you're making an impact. So find an area where you think you can make an impact and put your effort into that area.
Thank you very much. Thank you for this great advice and for this fantastic talk. It was really great to have you here today. And thanks everyone for participating.
Okay, thank you very much, Julia.
Thank you. Have a great day. Bye-bye.
Thanks.